All right, we're going to talk about today is how to calculate a definite integral and area in the curve by using the limit definition of an integral. Now, just so we know is that for some of you are probably thinking, well, what integral is just the antiderivative. Well, really, yes, antiderivatives can be used to find integrals, but when you're actually calculating an integral, we really are finding the area under the curve. And for many times, what we did was we found the area underneath the curves by using an approximation method known as Riemann sums. And when we took a particular Riemann sum, so if I had this parabola, and we're going from -1 to 1, and we would find this area right here, we would split this into a very small number of rectangles. So let's say we have 4, and so if we did 4, we would realize that, okay, we have to break it down into halves. So if we did a right Riemann sum, I would have like, okay, this one going over, okay, and then I would have 0 going like that, then I would have this one going over, all right, obviously this would be here, and then we go to 1, and we would have that one going over here, and we'd find this area, all right, and it would approximate, but we would be losing some area beneath the curve, and we would be gaining some area of the curve. So the question is, how do you find a definite, all right, area under the curve, or a definite integral? Now, in order to find a definite integral, what we're going to do is we're going to use, instead of just having n, because in actuality, we should know that if we keep on adding, all right, more rectangles and make these rectangles smaller and smaller and smaller, all right, we get the true area in the curve. And so how many rectangles we want? Well, we want to have an infinite number of rectangles, So how do you get an infinite number of rectangles? Well, knowing that we have our area formula, right here of our Riemann sums, where we take f of x, our height, times our delta x, which is our width, and we add all those rectangles together, depending on the number we want. Well, what we're going to do is we're going to take this and we're going to make it, and we're going to take n going to infinity, So we're going to have infinite amount. So in doing so, what we have then is we would have our delta x, I'm just going to put that in front, and then our f of x right there, and we're going to write this into some sort of notation. So we know that delta x equals b minus a over n. And now the question is, we're going to use a right Riemann sum to do this. Now, remember, a right Riemann sum, if I have this particular example, a right Riemann sum is we take our a value, so in this case, -1 would be a, this would be our b. And what we would do is we would take this value and we would add preceding values of delta x away from it. So if I have this right here, whatever delta x is, in this case, this is delta x, b minus a over n, a, or I would say, okay, well, if delta x, just to give it more concrete value, if it was 1/2, well, I would take -1 plus 1/2 to give me my first value for, all right, a, all right, our height. Plug in there. All right, so that would be like -1/2, and I would plug it in there. And then we go to the next one. So the second one, we multiply that by 2. So we go 2 delta x's away, so I get the 0. Then we go to 3 delta x's away, and I find my next one. And then we go to 4 delta x's away, and we have our various 1, 2, 3, 4 areas. Now, in this case, I'm going to be taking an infinite amount. So how would we write this out? Well, in order to find a definite integral, all right, I'm going to write out what this would look like. So we would start here. We would I equaling 1. So I'm going to start with our first one. We have n going to infinity. We would have 1 minus -1 over n, because our n is infinity. So we're just going to put n. And our f of x, so we would have f of -1 plus I being whatever this index is, times our delta x. So it'd be 1 minus -1 over 2. And we put that, and that would be good there. So if I put this into context of x squared, because that's my f of x, what would that be? And I'm just going to simplify this. We would then have n, I equaling 1. We have the limit as n approaches infinity. We would have, this would turn out to be 2 over n times, well, what's f of x? X is x squared. So I'm going to plug that in for all the x's of f of x. So it'd be -1 plus I times 2 over n, that quantity squared, because that's my function. And that is my Riemann sum. Now, so what would this look like for indefinite integral? Well, for a definite integral, we would see this and we'd say, okay, I am finding the integral, so that would be my sigma notation. So this would actually equal the integral from -1 to 1, all right, of x squared dx. What is the dx? Well, the dx is this dummy variable because, as we know, if when we take limits as n goes to infinity, 2 over infinity approaches 0. And so what we have here is an infinite series, all right, that converges, and it's going to converge to a value. So this approaches 0, but it won't be 0 times a number. It actually will approach a value. And so because this doesn't have any value, we're just going to call it dx. So dx is actually, all right, our delta x, which is a dummy variable. So it's our differential, which is approaching 0. Okay, so it's a very, 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 very small value. And then we have delta, or x squared, which is our function, okay, where we're just going to be plugging in values, and that's how we can figure this out, okay? And so that's how these two are correlated. Well, let's try another one. So write an equation for the exact area of the curve for this. Now, I can write my integral. The integral would be from 0 to 2, all right, of f of x, so x squared plus 1, so that's my f of x, times dx. Okay, so using this, let's break this down. So we're going to have the limit. So we're going to write this using sigma notation. All right, which is x n. We have n approaching infinity. Okay, n approaching infinity. We're going to have our sigma notation. We're going to have n, so we have an infinite amount of rectangles. We're going to start with our first rectangle. We're going to have our delta x, so that's our dx. So we're going to find our dx. So our dx is going to be, all right, 2 minus 0. So delta x is going to be 2 minus 0 over n in this case. So that's going to be 2n. Okay, so that's delta x. And then we're going to have our function. So our function happens to be this. So I'm going to plug in this value. Now a is 0 in this case. So what we're going to have is 0. I'm just going to put brackets around here because we have two different things. So we have 0 plus I 2 over n squared plus 1. There you go. When this could be simplified just to I times 2n squared if you want to do that. But there we go. That's it. And that's how we have our definite integral. Okay? And so as I stated before, this brings us to the definite integral. All right, no more estimating for us. So when we have this right here, this equals this. So the integral, this is Roman sigma. All right, lower limit of integration is a. All right, upper limit of integration is b. Okay, that will help us find our delta x. All right, n going to infinity. Our dummy variable, because we know this approach variable, is our dx. It's a variable, what's known as our variable of integration. That's where we're integrating it to. This is how we approximate what delta x is going to be. And then f of x, that's our height of our integral. And that is this part right there. But we can get rid of this because we can just make it there. And so, all right, how does this all translate to antiderivatives and known as property of the fundamental theorem? Well, this all boils down to, my friends, is that when you have this in finding areas, we can use the transitive property in essence, where we find the integral from a to b of fx dx equals the integral from a to c of fx dx plus the integral from c to b of f of x dx. So if c is in between two, the area from a to c plus the area from c to b will give us the area of the whole. In the same way, if you integrate in the opposite direction, so if you can go from a to b of f of x, well, if I switch this around and go from b to a, I'm essentially going in the opposite direction, so I'll have an opposite area, okay, opposite area. And then finally, what that brings us to is this little thing, is that part 1, all right, the integral from a to b of f of x dx is really the antiderivative, or the area from b minus the area from a. Strike through those two, where a of x is known as the antiderivative of f. All right, antiderivative of f. And that is what we know. Okay, and you want to write that down. So how does that work, or why does that work? Well, let's just say I have a really simple integral right here. If I have this right here, I go from the integral from 2 to 7 of 8x. Well, 8 is a constant, and I want to take this integral. Well, I realize that the area is going to be, all right, well, the area from 2 to 7. So I'm just finding this area right here. However, what we realize is that I can take the integral from, all right, um, 7 to 0. So why would I include 0? Well, from 0 to 7 gives me the whole. So I find the whole value right here, the whole value right here. Okay. And now normally what we do is if I take this whole value, I want to subtract this value right there, this value right here. Okay. All right. And so I'm going to take the value from 0 to, all right, 0 to 2. Okay. So from 0 to 8 minus the integral from 0 to 2, I realize that I find the area from a to b minus a to b. But if you also know is that this is true, this works out, is because I can take this right here, 8 dx. And because of using this other property, notice that this is not transitive, but I can verify that this equals because if I flip this, I can go from 0 integral from 0 or 2 to 0, all right, which doesn't really make any sense, but we know that equals the integral from, because these match, 2 to 7 of 8 dx. And there we go. So we just proved the fundamental theorem of calculus. Okay? All right. So 2 different ways of going through this, kind of reviewing. All right. We know how to find a definite integral by using the limit definition of the Riemann sums. All right. Where n goes to infinity, we have our delta x. Okay. And we have our function, which is a right Riemann sum, a right RAM. All right, right RAM, where a is the lower limit plus our intervals. So how do you find right RAM? You have to plug in f of a plus, all right, I of delta x, okay? And we're going to do that each time, and that's how we find that right RAM, okay? Well, I hope this helps you out in finding definite integrals and using integrate notation and also using the limit definition. All right, good luck and God bless the rest of the problems.